Hello there. This lesson, moving on from absorbed dose, this lesson's called equivalent dose. I'm just going to give you a little bit of advice like I did last time. If I write something here on the whiteboard, you'll need to get that into your red jotter. If you find writing difficult, you'll need to get possibly some assistance. Take a screenshot of every page, and I'll give you a warning before I'm just about to rub everything out. You can pause the video, get a screenshot, save it if possible, print it out and stick that in your red jotter as well. There's a bit of writing to do today, unfortunately. Okay, so what we're going to do is we're going to put together a couple of ideas from the last few lessons, and one of the ideas we're going to look at is this thing called ionization. And the other one we're going to look at is absorbed dose. Okay, now it's important that we keep the absorbed dose as low as possible in terms of humans, living cells being exposed to radiation. The less absorbed dose, the less energy that cells are taking in, and the less energy that they take in, that's got to be a good thing. We've also got to try and keep this ionization thing as small as possible, because ionization is when electrons are knocked off atoms. Now, if electrons are knocked off atoms in living cells, then those living cells could be damaged, or if there's enough cells that have electrons knocked off, the cells could be killed, and that's not very good either. So we've got to take into account how much energy and how many electrons are knocked off. Okay, so we've got this thing called equivalent dose, and equivalent dose takes into account both of these things. It takes into account the ionization, and it also takes into account the absorbed dose, and we want both of these things to be kept as small as possible. Now, you should remember that ionization is best caused by alpha radiation. So alpha radiation causes the most ionization. So cells that have lots of ionization taking place are going to be damaged or killed easily. So it's alpha that causes the best ionization, causes ionization the most. So it's alpha radiation that will damage or kill cells most easily. So alpha radiation is particularly dangerous because it causes a lot of ionization. And if you remember, when we did the ionization work, we said that things like beta and gamma didn't cause so much ionization. So if they don't cause so much ionization, they can't knock off that many electrons, and so they can't damage that many cells. Now, no radiation is good for you, but we need especially to keep alpha radiation away from living cells, and we need to keep beta and gamma away as well, just because it's good practice. Okay. So alpha's the worst at causing damage or the best at causing ionization. You've got to remember which one's which. So I'm going to write down worst for damage or best. That's the most ionization is caused by alpha. Okay, so let's just have a look at some sort of example. And let's say and I'm not going to say what the units are. Let's say we've got one amount, one blob of absorbed dose of alpha. And we want to compare that with 1 unit of beta. Okay, now because alpha causes more ionization, 1 unit of absorbed dose of alpha is more dangerous than 1 unit of beta. And what we've, in fact, scientists have actually found out that not only is alpha more dangerous, it's about 20 times more dangerous, 20 times unit for unit of absorbed dose of alpha. Unit for unit, alpha is 20 times more dangerous than beta. So it's almost as if you could have 20 times the amount of beta radiation, and that would cause the same amount of damage as 1 amount of alpha radiation. You don't want any of this absorbed dose really at all, but if you had to be exposed to it, if you had to make a choice, what are you going to go for? Are you going to accept a unit of beta or a unit of alpha? You'd go for a unit of beta every time because it's not nearly so dangerous. So it's 20 times more dangerous, alpha, than beta. And it's also 20 times more dangerous than gamma. And there are also some other types of radiation, common types of radiation that people using radiation would come across. I say common because none of them are, you want them to be that common. But we'll look at how scientists have managed to put these in a list to say this is the most dangerous and by how many times more is it the most dangerous. Okay, so we're going to make a table and you're going to copy this table into your book. You will want to remember as well that this table of numbers I'm just about to give you, you'll find them on the data sheet. You don't need to remember these numbers for exam purposes, but I'm just going to give you them here so you've got them to refer to in your jotter. So that would be the first little bit of work that we've got here, because I'm going to rub that out and we're going to have a look at this table of how much or how many more times dangerous is alpha than beta and gamma and some of these other types of radiation that we've not talked about yet, that especially occur in nuclear power stations. And of course, not everybody works in a nuclear power station, but if you do, you need to know which ones to definitely keep away from. Even though alpha can't go through your skin, we're talking about the effects on living cells. Remember that your skin, your outside layer of skin's dead already, so you can't make a cell worse than being dead, and the alpha would be absorbed by your skin and wouldn't cause any damage. It's when these types of radiation get inside your body that you need to be really careful, because that's where all the living cells are. And wherever you've got living cells exposed to radiation, they're going to get damaged the most. So things like your eyes are living cells, and their eyes are on the surface. There's no dead layer of cells on the outside of your eyes compared with hands and feet. Hands have got really thick dead skin, and probably the thickest layer of dead skin you have on your body is on the soles of your feet. So you can almost afford to get lots of radiation on your feet, but very little on your eyes and things like your tongue. And you certainly don't want to breathe any of these types of radiation in, because they can get in your lungs, which is full of very sensitive living cells. So that's the first little bit of stuff that we've got here. So what scientists have done, I've mentioned this number alpha 20 times is 20 times more dangerous than some other types of radiation. This number 20 is what's called a weighting factor. So this could be a little side heading, radiation factors for radiation, and we'll make a table. So we've already mentioned alpha is 20 times more dangerous than beta. So if it's 20 times more dangerous, we'll give alpha the number 20 and we'll give beta the number 1. And then we'll also give gamma the number 1 as well. So alpha is 20 times more dangerous than beta and gamma. So these are common types of radiation that are around us all the time in terms of background radiation. I've mentioned before that if, depending on your job, you might become exposed to other types of radiation, and some of these other types, which are not found in nature very easily, are things called fast neutrons. And these are in power stations, along with things called slow neutrons. So these are also found in power stations. Well, what sort of power stations? Well, nuclear power stations, where they use nuclear energy to generate electricity. So you'll get these in power stations. And if you haven't got room to write that in your book, because you'll write over to the left-hand side, then put it over on the right-hand side. So you find those in power stations. The other one that's very common, but you don't find this walking down the street either, but are very, very common, are X-rays. And where do you get X-rays? You get them in hospital or from the dentist. So these are found in nature. These are only in power stations. There's only a couple of power stations in Scotland. There's one in Hunterston on the west coast near Glasgow. There's Torness on the east coast near Berwick, south of Edinburgh. I've mentioned this before in a previous lesson. There's a power station that used to be in Thurso, but they've turned it off and they're now taking it apart. That's called decommissioning. Decommissioning is where you take apart a power station that's been in use. And the other place, of course, where you'll find these types of neutrons are in miniature power stations that are on board nuclear submarines, which work out of a place called Faslane, which is also to the west of Glasgow. Well, apart from that, we want to know what the numbers are. Fast neutrons, because they go quite fast, cause a bit of damage. Slow neutrons, not as much. And X-rays are in the same group as like beta and gamma. They've got the number 1. So we don't have any numbers less than 1. We just say, right, the least dangerous are radiations with the number 1. Slow neutrons are 3 times more dangerous because they cause 3 times more ionization. Fast neutrons, more dangerous still because they cause 10 times more ionization. And lastly, alpha, the most dangerous to living cells because they cause 20 times more ionization than some of these others as well. So I'll remind you that we don't need to remember these numbers. You'll need them for doing problems that we'll be looking at in a bit, but you don't need to remember these in tests and exams because you get this information on your data sheet. And the data sheet or the data tables are just lists of information with numbers that go along with them, like what's the speed of light, speed of light, 3 times 10 to the power of 8. Anything that's got a number is found on the data sheet. Formulae are found on what's called the relationship sheet. So there's your second page if you're pausing, taking screenshots, printing out, that sort of thing. That's your second sheet now for getting stuck in your book, or if you're writing, then just get it all copied in. And lastly, I've already mentioned this, but I'm going to write it down, is the danger caused to different tissues. Now here's a word, susceptible. How do I spell susceptible? What does that mean? Susceptible means that certain parts of the body, like eyes, are going to be damaged more easily by radiation than skin, for instance. Skin not affected because it's dead already. So eyes, tongue, anything that's living are more susceptible than some others. But really, it's just try and keep these things away from all parts of the body. And I've already said, like things like your feet, the living cells that are in your feet, because the soles of your feet are so thick with dead skin that the living cells behind there are not very susceptible. And same with the hands, your palm of your hand, it's quite hard skin. And so the living cells behind those are not as susceptible. Okay, so to summarize this then, this first bit, a wee summary, the danger to radiation is dependent on three main things. And the first thing is the absorbed dose. The more radiation dose you receive, the more dangerous it is. So absorbed dose greater amounts of radiation, or to be precise, radiation energy, so greater amounts of radiation energy will cause more damage, and we know that that's called absorbed dose. The type of radiation, for example, and this gives our idea of things called radiation weighting factor. And lastly, the type of tissue. That's exposed. And we know that eyes are much more easily damaged. And that's just because your eyes are open, facing to the world, and a layer of live cells right at the front exposed all the time. You can stop your tongue by getting exposed by keeping your tongue in your mouth and keeping your mouth shut. But you'd have to keep your eyes shut all day long. It'd be difficult for some people to keep their mouths shut all day long, I suppose. No names. Right, okay, so a summary to say what the dangers to living body tissue depend on: absorbed dose, type of radiation, and the type of tissue exposed. There's your third page, and your third page needs to be screenshotted, if that's a word, or written out If you're just writing, then you just continue writing in your book, one thing after another. So I'm just going to get a mouthful of tea. And this can get rubbed out now, and we'll move on. So we said that this is entitled equivalent dose. So we're now going to say what exactly equivalent dose is. Equivalent dose is defined as, now what does defined as? It means what is the meaning of, if you looked up in a scientific dictionary, you'd find the meaning of equivalent dose. And this is it. Now, I've written radiation weighting factor, the three words above each other. That's just because I've run out of space. If you've got space to write radiation weighting factor going across there, then that's fine. Now, we need some units. We already know that absorbed dose is measured in grays from last time. And we know that grays has a abbreviation of capital G, small y. Now, radiation factor doesn't have a unit. It's just a pure number. It's just a number. And where do you get that number from? Well, you look it up in that table where alpha's 20, beta's 1, gamma's 1, X-rays 1, and fast neutrons 10, slow neutrons 3. So it's just a number. Now we need to know that equivalent dose is measured in a new unit, in a unit called sieverts. Sieverts, S-I-E-V-E-R-T-S, sieverts. And sieverts has an abbreviation as well, which is SV. And where we have words, we can replace words with letters. So the letter for absorbed dose, as you already know, is D, because we did that last time. The radiation weighting factor is W for weighting, and an R for radiation. The letter F doesn't appear in it, so it's radiation weighting factor is WR, and the letter for equivalent dose is the letter H. I have no idea why they chose the letter H. I think it couldn't have been E, because we know that D is E over M. D, absorbed dose, is energy divided by mass. So we couldn't use E for equivalent dose. We couldn't use D because we've already got D for dose. And I think, they just chose H. Got no idea what H really stands for. But the formula is H equals D times WR. And we can put that in a triangle. And you can add triangles to the back of your red jotter if you're collecting them. And there's the triangle that we want. Okay, so there's how do we work out something called equivalent dose? We take the absorbed dose and just multiply it by the number from the table. So I'll give you a couple of examples. These are quite simple. There's another screenshot for you. Okay, so a couple of examples coming up now. Okay, so what's the equivalent dose if an absorbed dose of 10 micrograys of alpha is absorbed? We're not going to mention any different types of body tissue. It's just that it goes into live tissue and it can get absorbed. And this is the amount of absorbed dose. We want to make that as small as possible. And we see alpha, we go, oh dear, alpha, that's not too good, because we know alpha is quite dangerous, 20 times more dangerous. So we'll do our TUP for now, which will give us the table. What's the equivalent dose? I don't know what the equivalent dose is, so I'll put H is a question mark. I'll put D is the absorbed dose, which is 10 milligrays. And I know that the radiation weighting factor for alpha is 20, because we've already got that in our table. Okay, so what do? We do the formula H equals D times WR. And I'm not going to change the units here. I'm just going to keep this very, very simple. And I'm going to leave the milli there. I'm not going to divide by 1,000 or multiply by 10 to the negative 3. I'm just going to leave it as that, just so you get an idea of what's going on here. So I've got 10 milligrays, and I'm going to multiply by the weighting factor, and 10 times 20 is 200. Because that's milli, the answer is going to be milli, but the units now change to sieverts, because as soon as you take your absorbed dose in grays and multiply by a weighting factor, we get a new unit called sieverts. And in this case, we've got milligrays times the weighting factor. So my answer is going to be millisieverts. So that's 200 millisieverts. Example 2. It's pretty much the same. What is the equivalent dose if an absorbed dose of 10 milligrays of beta is absorbed? Okay, we already know, you should be thinking ahead of yourself here. You go, oh, right, alpha, I know the number for alpha is 20. I know the number for beta is 1. So what we're going to do, we'll just do what we're supposed to do, write down everything in the table. And we would look up the weighting factor for beta is quite simply the number 1 for beta. That's from the table. So I can now do H is D times WR. And I've got my 10 milligrays. I'm not going to change the units again. I'm just going to do the same here. I'm going to multiply 10 by the weighting factor, which is 1. And that gives me 10 millisieverts. Okay. Now, what would happen if you were very unlucky to be exposed to 10 milligrays of alpha and 10 milligrays of beta all at the same time? That would be pretty catastrophic if you got both lots of radiation at the same time. What would be the total equivalent dose if you had both of those absorbed doses? The total equivalent dose would be that 200 equivalent dose there, and this 10 of equivalent dose here, and you just add the two together. So you'd have 210 if you were exposed to both of those at the same time. And that's going to be the third part, is where we're just going to write that down and add the two together. So that's another page done for you to get a shot of if you're not writing it down. Hopefully, since I've started putting up these videos in YouTube format. YouTube's a lot easier to rewind, to stop, much easier than Google Meet. So I'm not doing any more Google Meet videos. They're all coming out as YouTube. I'm not going to even post up the Google Meet videos anymore. It's just going to be YouTube. Right, so number 3. I suppose it ought to be consistent. If I'm going to put the symbol for alpha, I may as well write the symbol for beta. I was going to write the word out there, BETA, but to be consistent. So in the unlikely event of receiving both alpha and beta in example 1 and 2 together, what would be the total equivalent dose received? Well, we already know that we've got alpha is 200 millisieverts and beta is just pure and simple 10 millisieverts. So the total would be just add those two together and you get 210 millisieverts of total radiation from both of those at the same time. Okay, now how big is a sievert actually? So a sievert's quite a big amount of radiation. You wouldn't go anywhere near the sort of places where you could receive a sievert. So I'm just going to give you some idea of how big sieverts are by relating them to a common thing, a banana. Okay, so a sievert, one sievert is a huge equivalent dose. So we often use millisieverts, which is what we've got here, millisieverts, or microsieverts, and it's that funny U-shaped symbol with a long tail, microsievert. Now, what is a millisievert? A millisievert is 1,000th of a sievert, and a microsievert is a millionth of a sievert. Okay, sievert's pretty huge. So let's have a look at some common sizes of equivalent dose. There is one of these numbers that you will have to remember, but you don't have to remember anything about bananas really. So there's another page for you, and I'm just going to finish off with bananas. Because bananas actually contain a very important element called potassium. Potassium is really important for healthy growth of your body and maintaining what's called a correct electrolyte balance or correct salt balance in your body, potassium. And some of that potassium, 99% of the potassium that comes in a banana is not dangerous at all. But a very small percentage of the potassium is in fact radioactive. It's what's called a radioactive isotope. And most normally occurring chemicals that we have around us have radioactive equivalents. It's the same chemical, but it's radioactive instead of being stable or non-radioactive. So bananas contain a very small amount of radioactive potassium. And how much? It's about 0.1 microsievert. So if you eat one banana, you're actually eating 0.1 microsieverts of equivalent dose of radiation. Now, if you just wander around, if you never touch a banana, I don't eat bananas ever, but if you just walk around, any member of the public walking around will be exposed to what's called background radiation. So the normal background radiation in a day how much would you get from that? Just walking around for 24 hours, going to bed, not even walking around, going to school, going on the bus, playing out on the field, sleeping. You are continually exposed to background radiation that we've talked about. And how much radiation is that? That's about 10 microsieverts per day. And now to get the equivalent from bananas in background radiation, you'd have to eat 100 bananas per day. So all I'm doing is trying to give you an idea of how many bananas you'd need to eat to get varying dosages of radiation. You don't need to remember these at all, but here is one that you need to remember. So I'm going to do this one in green, okay? And the normal yearly dose. Now, why am I writing this for members of the public? Because most people who wander around aren't getting exposed to radiation in power stations. They're not working in hospitals with x-rays. You might go into hospital or go to the dentist, and you probably wouldn't have more than about one x-ray in a year, unless you've got a lot of trouble with your teeth or you're forever breaking bones in your body. So we can add in sort of x-rays to members of the public. But if you take all those things that we looked at before, background radiation, and you made a pie chart of that, then the number that you need to remember is 2.2 millisieverts of radiation in a year. And that's a limit that's set by scientists that you should not exceed. So if they're going to find out if you're likely to exceed that, this is where you take these radiation counters that we talked about before, and you can put them in public places like schools. And Highland Council will have to make sure that in a year, if you go to school for 6 hours a day for 200 days in the year, that you must not exceed that. And if there's a danger that the amount of radiation that you're getting from spending 6 hours in school a day for 200 days in a year, if that's likely to be more than that, then you've got to take steps to make sure it's reduced to below that, because you've still got x-rays and things on top of that. That is equivalent to, and again, you don't need to remember this, this means you would have to eat 22,000 bananas per year. So although bananas do contain radiation, it's a very, very small amount compared to the amount of radiation that you're exposed to just by sitting at home, going to school, catching the bus, playing out on the field, going shopping in town. That's the amount of radiation you should not exceed. Now, if you want to know about, and you should have a read, if you want to know about other places and what constitutes harmful levels, that's not harmful. We live with that. We live with that for the whole of our lives, and it's not a danger because it's so small. and any amount of cells that get damaged or killed is such a small number in your body that your body manages to cope with that. But if you want to see what sort of levels of radiation you might get from various things, then have a look in the course notes. And the course notes on page 12 will give you a big table. You don't need to remember these, but the course notes on page 12 will give you a table of levels of radiation. And there are some numbers. It will tell you how much radiation you could get. Let me just have a quick look, see if I can find page 12 on my screen here. I can't because I've got rid of it, but you can have a look at page 12, and it's something like, a whole sievert, one sievert would give you radiation poisoning. Somewhere that sort of level of radiation would be pretty dangerous. So have a look for those. That's the only one you need to remember. There are other limits for people like me. Why is there a limit for me that's not the same as this? And that's because I'm a physics teacher and I work with radioactive materials, and I'm allowed to be exposed to a higher level of radiation than you are in schools. There's laws about what you can do. You're not allowed to go near radiation. You have to keep far away from it. I have to keep sources pointed away from you. Even for me, I need to pick up radioactive sources with tongs and wear a coat, a white coat, to try and cut down the amount of radiation I get exposed to. But I am allowed to have a slightly higher number. Radiologists in hospitals and people who work in nuclear power stations, they're not members of the public. They're working with radiation, and this number is a little bit more. And again, you'll find those numbers in the course notes on page 12. So refer to that, please. Okay, so I've given you some examples. There will be an assignment, and the assignment will be looking at some more examples similar to the ones that you've done, and I'll be posting up information about those shortly. And that's it for this lesson.